Good morning. I'm the chair of the jury and Professor Long from Sun Yat-sen University. So before we start, I would like to introduce our jury. First one, Professor Shi Ling from Zhongxin University, and Professor Guan Qi-shen from NTU, National Canada University, and also Professor D101 from D101 PF4, and Professor Li Yingde from University. All right. So then next we are going to let the team to introduce themselves. Let's start with the reporter for the first stage.
Good morning, we are Team Banana. I'm Nick. This is Felicity. This is Max. This is Vincent. And this is Vincent. Thank you.
All right. And next we will let the opponent to introduce yourself.
I'm D101 from National Zhanghua Senior High School. And this is Zhang Jiao, this is Shen Xiangyuan, and this is
All right. Next we will have the juror to introduce your team.
Hello everyone. We're team members. I'm Orange, and this is Rosie. This is Liu Zhenghao. This is Ling Chen.
All right. Finally, we have observer please introduce yourself.
Good morning. We are team Mindao Meiyan, and we are from Mindao High School. And I'm the captain. I'm Roger. This is Michael, and this is YC, and this is Alan, and this is Shou.
All right. Thank you. So now we are moving forward to physics 5, and we are on this stage 1. And we can start, and opponent can start to challenge the reporter the problem. We have 1 minute. Question number 4. Okay, 1 minute to decide.
We accept that challenge.
All right, the reporter accepts the question. You have 5 minutes to prepare.
to make the rod spin. And the magnet will be put here to let it point. This is our experimental process. We film it and we use tracker to track it, and then we analyze it. This is just to emphasize that we have made lots of time to make it more, it is more reliable. So let's talk about the theoretical model. First, this is a free body diagram. There are a few of force that is used. First, the weight of a magnet, and the second is the friction generated to resist gravity. Here. And the second will be the forward force. The fourth will be the magnet force. Okay, this will F of C will be the friction, and the F prime is also the friction. And the normal force. So the reason why the magnets climb up, as you can see, it doesn't just climb up straightly. It actually spins and spins up again and again to climb up. So let me explain this phenomenon for you. First, this is the original state as the rod hasn't spins. And because the rod spins, so it spins to the left. And this is the pivot point. So the force will make it has the angular acceleration and spins up. However, the rod keeps on spinning, so it goes to the left again. As it repeats this motion again and again, there will be one point that when the pivot point, when the normal force cannot go even more left. So it reached the maximum of the angular acceleration. So it spins up again and back to the original state. So the climbing motion is actually this and spins up again and again. And it's what you see as it climbs up. Let's see the animation. So this is what we call one cycle later. So the reason for why the magnet will climb up. Okay, and now I need to talk about the pivot point. We haven't mentioned why there is a pivot point. We cannot see if there is really a pivot point here since the force is invisible. So now we need to talk about why we need to prove that there is really a pivot there, and we will talk about it later. So this is the motion model. The first equation is the balance on the x-axis, and the second equation is the torque. And so if we merge the first equation and the second equation, we can get the fourth equation, which is the angular velocity. However, we can see there is this angular velocity is this side. However, this makes the other direction. So we need to minus the angular velocity caused by this force. So the total will be here. And just to simplify the equation, so we make the approximation here. And then we can get the last simplified equation. So now we get the equation here. And as you can see, it is like there will be a period for this function. So here, these parameters we will use later can affect the period of this function. However, the theta, we don't know if the theta's function is theta of t, or it's just simply omega times t. So this is an unknown function. So these are the below parameters as we just listed. And here is the potential parameters, which means that these may affect the motion of this magnet. However, we didn't see it in the equation, so these will be the potential parameters. And now, the parameters we have mentioned analyze, so we didn't do that. And the third one, the coefficient of friction of the rod, is because different area of the same thing may have the different coefficient of friction. So we didn't do this parameter also. So now let's jump into the parameters. This is our assumption. So if the coefficient of, so as mu prompt increases, we assume that the maximum of the acceleration will get larger, will decreases, sorry, it decreases. However, it doesn't affect the period. And the second will be the radius of the magnet. As the radius increases, the maximum of the acceleration will also, it will also decreases. So, however, it doesn't affect the period also. For the rod rotate speed, which is the potential parameters, we only can assume that it affects the period because it is not in the equation. And also, just as the former one, we also can only assume that it affects the period. So now let's do the experiment. But there is one more thing I need to talk about. So we have talked about the pivot here. So to prove that there is really a pivot that we assume in the magnet, if it meets our assumption, then it will not rotate as we put it, what's that called, horizontally. However, if there isn't a pivot that we assume, then it will rotate even if we put horizontally on the table. So let's jump into the experiment. First, just to emphasize again, if it meets, then it will move. So for the video, as you see, if the rod keeps spinning, the magnet still doesn't move. So it is as
show the slipstick phenomenon. Can you explain what is slipstick phenomenon?
Slip.
Do you know slipstick?
It's like the magnet slips.
Yeah,
around.
that's the slipstick phenomenon at this experiment.
Yeah. I explained it by that.
Or you just on the phone and try.
It's just explained like this, but I was thinking like this spins up.
So you mean the slipstick will make the magnet to clap?
Yes.
Yes, I know. And the next picture.
Which
Yes. Oh, okay. One of your reports. What is this FV stand for?
is the just read it for you. The F4P represents a friction due to the relative size of the atoms. Yeah. First switching. Is there the friction?
Blue force and red force. What is the difference between them?
The blue force is the here and because it spins, so it gets the F of C and the
Okay, I'll check you. This blue force is the normal force or not? And what is this direction?
the
Thanks,
direction here is X.
Right. You can 3 minutes to prepare.
Okay.
是有些是可以延续的，就是会跟这个，就是这种这个就是它是这种然后就这一段如果一直拿着，你的决定是什么？你的决定。大会停的状态上，你说这个这边它一盘刚刚跟15，这边应该就变跳成2分45，就是这个15是占到他自己的时间，完全看好了。对啊，因为这是3个一起，对不对？那他如果是3个，等下就不绕这个对着切下来，这个是3个那就那如果预备太久，然后就站到它这个
Okay, I'm a owner, and my name is Daniel. My team is Huayme. I come from Zhanghua Senior High School. Okay. The kinetic magnet problem statement attach a rod assembled from cylindrical neodymium magnet horizontally to vertical ferromagnetic rod. You can see the motion of the magnet through vertical direction. When the ferromagnetic rod is squared around its axis of symmetry, the magnetic rod is being to climb up. Explain this phenomenon and investigate how the rate of climbing depends on the relevant parameter. Force and count for reporter. The strength, the chart clearly illustrates the information. Our suggestion is a more clear video because I see your phenomenon video. I can see this too far. I can see the magnet rotate, and the conclusion like data support. You decrease number of calculate and more focus on problem statement and its sleep stick. And you can finish the report within limited time. And you don't show your conclusion clearly. Okay, I want to accept question for reporting. Okay, what is FG and the brute force and red force? Let's talk.
Actually, the capital alphabet, which I haven't answered, is that the forward force is between is equal to the what's that called magnet force.
The meaning is if the magnet is like this and this is iron rod, the
It's
brute
not-
force will this direction.
Yeah, it's the normal force.
Normal force. Okay. And why is normal force at the bottom will be greater than those at the top?
Because the weight is here and it pulls it down a bit, so it will go. It will be smaller on the top.
So does it have torque and then is it torque? I said where is the pivot of this system? The magnet pivot.
If it is here, we will move it here. Yeah.
So does this pivot to the weight? Does it have the torque or not?
Can you rephrase it?
Torque. No torque.
A torque.
Torque.
Is there torque or not? We have it. I think we have it. Yeah, we didn't talk. It's because like we have talked about that like increasing the strength. Why we didn't do the parameters is because when this is too large, it will spin like it actually spins like this. And when it's too large, it makes it spin still like this. So we cannot actually analyze.
But I think it has torque. I want to use the whiteboard.
And I agree with that with Wilkins for it. It's just we didn't like really discuss about it. So if we can do it more, then I suppose we will do that.
And what's the random force direction? Point two.
This along the line axis.
Y-axis. Why? So just like this.
Pointing into the back because it's this. So there will still be a force that resists it.
And 14. Okay. You say the magnet will deviate from iron rod from here to there, from there to here.
The magnet. Yeah.
The contact line at the center by move to the left. So why it move to left?
Because the rod spins.
Must be.
Yeah, and it wants to.
Can you show me the force at the magnet?
The first of the magnet.
Because it moves because it has the force to push it move.
It's because this isn't moving. So when the rod moves, it's.
So you mean the red force push the deviate from its center?
It's because the magnet is not moving at first. So the rod, when the rod spins, it will move there. Yeah. From another perspective, it is because atmosphere. Yeah.
So atmosphere is one of the friction or not?
It is.
It is okay. And page 18. Page 30. Okay, so I see the point C of the represent. Where is point C?
Yes.
Or point C?
It's
So why you show the point C?
Why?
Why you mention the point C and then?
It's
Because I think it doesn't connect the iron rod.
it's the middle of the
Okay.
magnet. Yeah.
32. Page 32. What is the coefficient of friction of the rod?
This
Yes.
is the F of C. Because it contacts the rod, it is the friction of it, and the coefficient of the friction.
And then we come back. Slip stick. Can you draw the slip stick for the motion and the whiteboard to show me? Because I think slip stick will not make the magnet climb up. I think it will not. You persuade me it will climb. If the slip stick will make the magnet climb up. Why climb up?
It's because that here it moves like that.
I think rotate has two. If an object rotates, it will have a torque, but I don't see
It's
your.
because we take point C as the reference point here, and the torque we set here is this. So it gets the F of C here. That's the reference point is here. So the magnet spins up.
I think that's wrong.
Yeah.
Because the thing have contact line, magnet and iron rod always contact, right? I think the normal force at the top and the bottom are different. Do you agree with that?
Yes.
Why you show that? The different normal force and I think you have two force there. You have showing the force on this point. But it's because the magnet and iron rod are contact, so it will have a normal force. And the red F is friction, right? Normal force lead to friction, but you don't show the friction.
The friction is this, and this is what we just said is the atmosphere. And as you said, the normal force is smaller as the top. So we can, if we want to like push it into just a point, we will say that it is here, and the force, the friction will be moving here. So it makes the magnet rotate. It makes it rotate.
Okay. You still think the slip stick will make the magnet climb up?
Yes.
Okay. And have you considered the friction between the magnet and the wall? My wall is this orange shape.
Yes.
And this purple force.
This is purple forces.
Okay. And why does the experiment of the horizontal iron rod is include iron rod on the table?
Are you asking why or
Why you do this experiment? What you want to show me to know?
because we suppose that there will be a pivot here. So if the pivot here is caused by the normal force.
Yes.
So if our assumption is wrong, then and even if there is no, when the force on the z-axis is balanced, it still spins up.
Okay.
So it means our assumption it wouldn't rotate at this state. However, if it doesn't, then it moves up, no matter if there is balance.
And I have some question about your first experiment. If you don't use the wall, the magnet will climb up or not? If you don't use the wall, this is if the wall is disappear,
It climbs up also.
it climbs up also.
This is actually the other direction. So it is actually decreasing the acceleration, the angular acceleration.
What?
Because our direction here is rolling counterclockwise, and this is making a torque clockwise as a direction of clockwise. So it is actually the previous page. No, the previous page. Yeah, thank you. We actually counted it, we minus the acceleration.
Okay. So page 53.
Agree?
And can you explain why the wave at the highest rotate speed, its distance is shorter, but the lowest rotate speed when the low rotate speed, the distance between the two waves is longer.
I think that this here is wrong.
Or I want to say why omega affect the rotate speed.
And this is why we said it's a potential parameter, because it is not in our assumption. So we cannot, but I suppose that it's because the omega of the rod will make the friction gets different. Maybe.
Okay, so you doesn't understand why the omega affect the rotate speed.
We can only assume it.
The conclusion is the reporter think this stick will make the magnet to climb up, and you can understand why omega affect the magnet to climb up. Okay, it's my conclusion. Thank you.
As a reviewer of the first question, you said you mentioned that the magnet rotate.
Magnet rotate.
Did rotate. So it's magnet has angular acceleration?
Yes.
Okay. The second question, how do you define climbing rate?
Climbing rate.
Yes, because you have two motions and the speed are different.
Climbing rate is just simply the center of the magnet climbing up for the y-axis. We only calculate the y-axis.
Also, but you have two motions.
Two motions.
Yes, spin and split.
Oh yeah, so for the climbing velocity, we only consider the velocity on the y-axis. The spin is the angular velocity.
But you have two motions. Is the two motion velocity same?
No.
So you measure the two motion.
We measure. We both measure this.
How do you agree the definition of the reporter?
What is
Do you agree the definition of the reporter?
I agree, but I think it have explained exactly.
Okay. Okay. How the omega affect?
How the omega affect? And we suppose that the reason that omega affects is because as it spins faster, all the friction will change.
But you assumption that doesn't. In your assumption it doesn't affect.
Yes. So we said we didn't assume that it doesn't affect. It's because the simplified equation inside didn't have the.
So you did the experiment and you showed it affect.
Yes, it is potential.
Okay. So okay, the problem statement is the climbing rate, but you measure the acceleration.
Yes.
How do you measure the acceleration?
How do I measure?
Measure.
Measure.
You measure the center of the magnet. You,
Measure the
how do you?
acceleration. We measured the acceleration. We measured the.
Hands up.
the reviewer from numerical computation. The problem statement is that, and the key points of the reporter is the relevant parameters that affect the timing rate and the spin and split motion they observe. And the report summary, in their theory, they do the spin and split theory, and they explain they use a picture to explain it, and in their observation, they proved that there is a pivot between the rod and the magnet. And then in their experiment, they said that the magnet length is hard to analyze. So they believe they said that. Okay, and then is the coefficient friction. It will, the increase of the coefficient of friction will decrease the magnetic acceleration. And the magnetic radius won't affect the period in the theory, but it does affect the experiment. And the magnetic field won't affect the period. And that is the overall of the report. The pros is that they use pictures to show the photos to show the experimental setup, and they have clear graphs to explain they use clearly picture to explain the phenomena and the spin split, and they have smooth transitions and the real parameters of the things on their slide. And the cons is that they didn't investigate the theory further, and they didn't prove that some parameters don't affect, or they did experiment to do it, but they didn't explain the deviation of the assumption and theory further. And then is the overall of the opponent. The pros is that they clarify the misunderstanding well, and they point out the mistakes of the theory. But the cons is that they are too focused on the theory. They did very, very few focus on the experiment, and that they can express their question in an easy way. And they are too focused on some problem, and they didn't discuss the experiment and how the parameters affect results. And then is the discussion. The opponent asked that are the torque in the experiment, and the opponent said it has, and reporters said they didn't talk about it, so they guess they have. And then is why the center of the mass move. The opponent asked reporters to show the graph, and the reporters said that the magnet is moving not fast, so when the rod spins, the center will move. And then the influence of the slipstick. The opponent said that it won't make the magnet climb out, but the reporter draws the curve button this way. And then, will omega affect? The reporter said no, but their experiment, yes. And is there angular velocity constant? Our question. The opponent said no, and the reporter said yes, and the reporter said no, and we think no. And how define climbing rate? The opponent agreed with the reporter that they define the y-axis. And we also agree, but they didn't mention at the report. And how does the omega delta impact? I think they should do the experiment. They should investigate it further when they found that it's not that.
And that is we are come to the remarks. First, we need to first clarify from the discussion we just had. These are the main points of our report. First, we had a sum for the moving model, and we have theoretical calculation of the model. And we to vary, but it complicates spin because of the weight of the magnet. Thank you.
All right. Next question of the jury. Please.
Question for you. Your theory based on the chain of the pivot point. So why is that pivot point?
The pivot point is because it's making the because the upper normal force is smaller.
What station is the point?
Sorry, can you repeat?
Why is the point instead of a line or a circle? Why is the point?
A point on the surface of
What's the
the.
origin of the pivot point?
Where's the origin pivot point? It's the normal force. It's making the normal force into a point. Like putting all the normal force, we simplify it into only the force coming from the surface of the rock.
You're increasing the interaction force, it should be the center of mass.
Sorry, can you say it again?
You apply the force on the body, it should be applied equivalent to apply to the center of mass, not at the edge.
No, then, because it's because the normal force here, because the weight here it pulls it down a bit. So the normal force here, the upper part is smaller and the down part is bigger. So if we want to simplify it into the force at one point, it will hit in the under the position.
All right. Any further questions from Jude?
You mentioned about the wall to constrain the rod to move vertically in that direction. Is there a wall to confine the rod, the magnet,
Yes.
while it is coming up, right?
Yes.
So do we have to worry about the friction between the magnet and the wall?
Yes.
Did you mention it? Maybe I missed it.
Yes. We have considered it in our theoretical model, and we also
I mean, what is the coefficient
the
between the magnet and the wall?
neutron here is the neutron here is the
Oh, that's the new part, right?
yeah, neutron is
Oh, okay,
just
okay,
is the
thank you.
All right. No further questions? I think we can give a score. Oh, you want one more question?
I have a question for you. Do you agree with her theory? Do you agree with her theory?
No, I don't.
No, I don't.
Then what do you think is a real theory?
Because their experiments didn't fit their assumption well, and if there has an acceleration, they only they have the acceleration total. So I think when the magnet declines further, and the velocity of it will be very big, or maybe when
I think this force diagram doesn't detail enough, so I think maybe know something to consider. So I don't disagree with you.
So you still lose the data is not reliable?
No, not data, it's force diagram. Because it can explain this smoothly. I think it doesn't understand enough.
All right. Any further comment? Okay. Then we move on to the score. Now we are to the score for the reporter. Ready? Ready? Okay. For the reporter, the score is 7, 9, 6, 6, 8. Now, sorry. Now, for the opponent. Ready? Okay. 6, 5, 6, 5, 6. Now for the reviewer. Right. Now for the reviewer, 6, 6, 6, 6, 7.